discussed how a periodic signal, be it a continuous time signal or a discrete time sequence, how a continuous time signal can be represented in terms of exponentials. Okay, so for example, if you have a continuous time signal xt, which is periodic with a certain period, let's say capital T. Okay, so there exists real quantity, real positive quantity, let's say capital T, for which the following relation holds, then we say that xt is periodic. Okay, so xt can always be represented in terms of harmonically related exponentials, complex exponentials. That is, you can express this in a form of linear combination of complex exponentials. So where these ak's are the Fourier coefficients, so these are also the strengths of such harmonics. So this can be written as e, j, k, omega naught, okay, into t. Okay, so k is the harmonic index. So the summation is over k. In general, k is going to vary from minus infinity to plus infinity. So I mean, you can have infinite number of harmonics. So you see, if you're going to expand this for a few terms, well, okay, let's suppose for simplicity k starts with 0 and goes to infinity. Then the first term is a DC term, a naught, plus a1 e to the minus j omega naught t. So that's your first order fundamental frequency, plus a2. So a2 forms the strength or the weight of the second harmonic, which is twice omega naught t, and this trend continues up until infinity if the signal is consisting of a very large bandwidth or large number of frequencies. So if it is periodic, well, it can always be represented in terms of its Fourier series expansion. Okay. Now it turns out that, okay, omega naught, since we are talking of periodic signals, omega naught is the fundamental frequency given by 2 pi by t. Okay, and if you notice, as t tends to infinity, as t becomes very large, then omega naught becomes equals to 0. Okay, I mean, as a limit, it tends to 0. That is, as you go on increasing the period, the fundamental frequency becomes small. I mean, the omega naught becomes small. That also implies that k omega naught, which is the harmonics, k omega naught is the harmonics, k being the harmonic index. Okay, it could be omega naught 2, omega naught 3, omega naught. This k omega naught becomes small. So the difference between the harmonics are small now. So it means in the Fourier spectrum, for example, if you're going to draw for the, let's say, magnitudes of ak, so okay, ak's can be complex quantities. So if you draw for the magnitudes of ak, as t becomes large, these Fourier coefficients, they become bunched together. Okay, they come closer together, and so they form the, for example, you can say that the number of samples or the Fourier coefficients are large, and they are going to become themselves, they're going to represent themselves as an envelope of a function which is a continuum, okay, which is a continuous function of frequency. That's the concept of Fourier transform. You see, the idea is, what Fourier reasoned was that, well, okay, we have already discussed how we can represent a periodic signal in terms of Fourier series expansion, in terms of complex harmonically related exponentials. Well, what about aperiodic signals? Okay, now there exists another broad class of signals which are not periodic, which are aperiodic. Okay, with finite durations. So, is there a way to represent them? Well, what Fourier reasoned was that an aperiodic signal can be viewed as a periodic signal with an infinite period. Okay, so it turns out if t is infinity, then the fundamental period is small, which means k omega naught is small, which implies that the Fourier coefficients, they are becoming a continuum. Okay, they are representing an envelope right now. These are large number of samples which are much closer to each other. So more precisely, in Fourier series representation of a periodic signal, as the period increases, the fundamental frequency decreases and harmonically related components, they become closer in frequency. Therefore, instead of having those discrete Fourier coefficients in the spectrum, we are going to have something. This is for when t approaches to infinity. You'll have the Fourier coefficients. If you plot the Fourier coefficients, you'll have a continuous plot like this. Okay, this is for t approaching to infinity. So as the period becomes infinite, the frequency components form a continuum, and the Fourier series becomes an integral. Well, that's a natural extension of the summation operation. If there are a large number of samples, then that becomes a continuum, and the summation operation becomes an integral. Both operations are linear mathematical operators. So what happens is that you don't have these samples. I mean, the samples of, for example, the samples of this envelope are the Fourier, if they are the Fourier coefficients representing the strengths of the frequencies contained in the signal, then this envelope function is representing the frequency itself. Okay, I mean, there are so many Fourier coefficients which are now closely spaced together, since k omega naught is very small. We have a continuous frequency function which we can call as x of omega. Okay, and well, where omega, we can write this omega as k omega naught. Can we do that? I mean, since k omega naught is very small, it becomes infinitesimally small as t goes to infinity. So this function is over omega. Okay, so x omega is the Fourier transform of a signal xt that is not periodic. Okay, or you can say that if t goes to infinity, well, okay, so what if t goes to infinity? Then I can say that I have another signal, call this x tilde of t, and x tilde of t is basically xt in one period, right? X tilde t is xt in one period, for example. Okay, so let's get more insight into this. To understand the intuition behind this, to gain some insight into the nature of Fourier series, let's consider the Fourier pulse. Let's consider a repetitive or a periodic pulse, which we have considered in example 3.5. So, to gain some insight into the Fourier transform representation, we begin by revisiting the Fourier series representation for continuous time periodic scale wave. So you can see this, the expression is as such that xt is 1, okay, when t is bounded by t1, okay, magnitude of t is bounded by t1, so it is 0 for t less than minus t1, and for t greater than t1 it is 0 otherwise. Okay, so, well, what happens if I let t goes to infinity, which is a period of this rectangular pulse? Well, then we only have one rectangle. What we are left in the time domain is only one pulse. That's it. This is x tilde of t, which is equal to xt in one period, which is equal to xt for one period, So you see, these are equivalent specifications. So either you can let t go to infinity. Okay, so this t by 2 minus t by 2, they go to infinity, so it moves towards infinity. Minus t by 2 goes to minus infinity. So you are left with only one pulse. So therefore, the two signals are equivalent in one period. So that's how you can make a periodic signal into an aperiodic signal. That's how the Fourier reasoned that. Well, if that is the case, then you can still go ahead and represent an aperiodic signal in parallel to Fourier series, how we represent a periodic signal in Fourier series. The difference will be that you will have a continuum of such representation in terms of Fourier coefficients, which are closely packed together, and it becomes a continuous function. Okay, so but just to see this more in an intuitive manner, we're just revisiting this example. So if you recall, the signal is periodic, again with period t, with the fundamental frequency 2 pi by t. And if you recall, in example 3.5, we evaluated the Fourier coefficients as such, where k is not 0. Okay, I think for a naught, for k equal to 0, the coefficient was the average of this rectangular pulse was over one period, so it was 2t1 by t. Okay, so the average of xt dt over one period is 2t1 by t. Okay, uh, so these two expressions are equivalent, you see, because omega naught t is 2 pi, omega naught t is 2 pi. So you can bring 2 pi here, cancel this 2, and you can write it as such. These two expressions are equivalent. Okay, this is for k not equal to 0. We have already developed this expression in example 3.5. Now, in the figure below, these are the plots for this. In figure A, we have t1 is fixed, so this t is 4t1. Over here, t is 8t1, and you can see how the DC coefficient, Fourier coefficient, is the strength is reducing. Okay, because as you're going to increase capital T, the strength is going to reduce. For example, for 4t1, this is half. Okay, for 8t1, this becomes 1/4. For 16t1, it's even less. Okay, so this plot is for t equal to 16t1. This becomes 1/8. So for 16t1, the DC coefficient is 1/8. And then you have the rest of the coefficient, because the rectangular pulse is also, you can see that xt is an even signal, is real and even. Xt is periodic, it is even, it is real, which means, which implies that your Fourier coefficients are going to be even and symmetric. Okay, this will be a minus k. So you can see the symmetry over here as well. The Fourier coefficients are symmetric. Anyways, the point is that these plots are the Fourier coefficients for tak. Okay, so you can bring this t onto the on this side, left-hand side of the equation, and you can plot this as a function of k. Okay, the harmonic index. So of the square wave for t1 is fixed, and there are several values of capital T. And the first plot is for t equal to 4t1. You can see that the number of samples, the Fourier coefficients are not, there are not much samples of Fourier coefficients, but these number of coefficients, they tend to increase as you go on increasing the period. In figures B and C, okay. So for part B, this is 8 times t1. For part C, this is 16t1. So the coefficients, they are regularly spaced samples of the envelope. Which envelope? That is 2 sine omega t1 by omega, this envelope. Okay, because if you replace k omega naught by omega, okay, then the envelope, if you bring this t on the other side, the expression becomes, so the envelope is tak equals to twice sine of omega t1 divided by omega. Okay, form of a sinc function. You can express this as a sinc function. You can see how this envelope represents a sinc function. So the thing is, if you go on increasing capital T, the period, then for the envelope tak, the samples they become more and more bunched together. Okay, so the spacing between the samples 2 pi by t decreases as t increases. Okay, so you have more number of samples and the spacing is decreasing. So an alternative way of interpreting the Fourier coefficients ak is as the samples of the envelope function. Ak's are the samples of the envelope function. Which envelope function? That is twice sine omega t1 over omega, where omega is k omega naught. Okay, since as we are increasing t while omega naught is decreasing, that means the harmonically related Fourier coefficients are coming closer and closer together. That is with omega thought of as a continuum variable. The function represents the envelope of not ak but tak, and the coefficients ak are simply equally spaced samples of this envelope. Okay, so this is the envelope. This is the envelope of tak. The samples are regularly spaced. Okay, these are the sampling interval is regular. It's the same. Difference between samples are same, but they're becoming more and more close together there because the capital T is increasing. Okay, so with increase in capital T, the difference in Fourier coefficients is becoming smaller and smaller. So also for fixed T1, the envelope tak is independent of capital T. You see in these figures. Okay, so let's consider this figure. The envelope is not dependent on t, right? I mean, the shape of the envelope is not dependent on t. It's only as capital T is increased, you have more number of samples. So for example, in the figure below, we again show that the Fourier series coefficients for a periodic square wave, but this time as samples of the envelope of Tak as specified earlier. So from the figure, as we see, as the t increases, or equivalently the fundamental frequency decreases, omega naught is 2 pi by t, the envelope is sampled with a closer and closer spacing. So these Fourier coefficients become closer and closer together. So for example, the main lobe width stays the same. I mean, the overall shape is preserved. Overall shape, the envelope is independent. The waveform of the envelope is independent of the period, but the number of samples are more. For example, this sample over here is twice the fundamental, but this sample is 4 times the fundamental. Then this sample is 8 times the fundamental as capital T increases. Okay, so again, these values are the same. This is for part B, this is 8T1. For part C, this is 16T1. So the shape of the envelope stays the same, but there are more samples which are bunched together, and we can think of omega as a continuous variable right now. So omega k, this omega, which is k omega naught, becomes a continuous variable because omega naught is a very small quantity, and k is increasing from minus infinity to plus infinity. Okay, which you can say over here, for example, 2 omega naught, minus 2 omega naught, 4 omega naught. It continues basically. It goes beyond that. So, but that's just as t is increased, you have more number of samples, right? And the shape of the envelope stays the same. So as t becomes arbitrarily large, the original periodic square wave approaches a rectangular pulse. So all that remains in the time domain is an aperiodic signal corresponding to one period of the square wave. All right. So this is what we are talking of. So you see, as t is becoming infinitely large, well, then x tilde t. So xt approaches to x tilde t form of a rectangular pulse. That is the only pulse in the time domain with infinite period but finite duration. Okay, the duration is again from minus t1 to capital T1, 2t1. Okay. So this is an aperiodic signal. Okay, this is an aperiodic signal. So xt is x tilde t. It's an aperiodic signal if its period is thought to be of an infinite duration. Okay, the period is infinite. So also the Fourier series coefficients multiplied by t become more and more closely spaced samples of the envelope, so that in some sense, which we'll specify shortly, the set of the Fourier series coefficients approaches the envelope function as t goes to infinity. So it becomes a continuum, right? And this is what is happening over here. As t is becoming very large, the samples of Tak are becoming closer and closer together, and then there will be so many samples that it becomes a continuous function of omega. So this is a continuous function of omega. So this is the Fourier transform. This envelope represents the Fourier transform, and the samples of this waveform are the Fourier coefficients, right? Are the Fourier coefficients of an aperiodic signal, or you can say they are the Fourier coefficients of a periodic signal with period infinity. Okay, and these both statements are the same. The samples again are reflecting the strength. I mean, for example, if you want to see how much over here, okay, let's see, this is omega naught, this is 2 omega naught. You take the sample over here, this is 2 omega naught. You want to see how much strength the second harmonic is contributing in the signal. You take the sample at 2 omega naught and see this for yourself. The value of, if I call this envelope as x of omega, then at omega equal to omega naught, what is the magnitude of what is the magnitude of this envelope function at omega equal to twice omega naught? So this is going to give you the strength of the Fourier coefficient, or the strength of the second harmonic that is contributing in the signal itself. Okay, so the samples again are the Fourier coefficients, or the strengths of the harmonics that are constituting the signal. Okay, so this example illustrates the basic idea behind Fourier's development of representation for aperiodic signals. Specifically, we think of an aperiodic signal as the limit of periodic signal as the limit of a periodic signal as the period becomes arbitrarily large. And we examine the limiting behavior of Fourier series representation for this signal. So in particular, consider a signal xt that is of finite duration. Over here, xt is a finite duration signal now, and that is for some number t1. It's finite, okay. So xt is 0 beyond t1 as illustrated in figure A. So from this aperiodic signal, we can construct a periodic signal x tilde t. X tilde t is periodic now, so for which xt is one period. So you see, for x tilde t, if so this is periodic with period capital T, and as you move this plus minus t to infinity, minus infinity, then x tilde t becomes xt as a limit. X tilde t is periodic, but xt is aperiodic. The difference is that the period is infinity. X tilde t period is infinity, or one period of x tilde t is xt, right? So as we choose the period t to be larger, x tilde t is identical to xt over a longer interval as t approaches infinity. X tilde t is equal to xt for a finite, for any finite value of t. Okay, so these are the same signals if considered for x tilde t in one period, or if x tilde t is thought to be of an infinite periodic signal. Okay, so part A is aperiodic signal xt. Part B is showing you a periodic version of the same signal denoted by x tilde t, constructed to be equal to xt over one period. Okay. Now let us examine the effect of this on Fourier series representation x tilde t analytically. So if we rewrite the Fourier series equation here for convenience with the integral synthesis equation for Fourier coefficients carried out over one period, this is the finite duration over which it exists. So either you can do it for one period, or you can do it for minus t1 to plus t1, where x tilde is non-zero. Okay, so over one period is minus t by 2 to plus t by 2. Or you can write this from minus t1 to plus t1. That's where x tilde t is non-zero. So in terms of Fourier series representation, x tilde is periodic. So we can always represent a periodic signal if it satisfies certain, for example, Dirichlet's conditions. If it is of finite energy in one period, etc., doesn't has infinite number of discontinuities, so which is the case in this signal. Okay, the Fourier series is convergent. So given the Fourier series is convergent, we can always express a periodic signal in time domain by linear combination of complex exponentials, and these exponentials in turn are harmonically related with the strengths AKs. Okay, now AK are the Fourier coefficients which are given by the synthesis equation. Sorry, the Fourier analysis equation, which is 1 over t. 1 over t is the period, then x tilde t e minus j k omega naught t dt. So now, since x tilde t is xt over one period, and also since xt is 0 outside this interval, the Fourier coefficients, they can be written as, so in one period it can be written as, so okay, xt was your original signal from which we constructed periodic version of it, x tilde t, by repeating it at a finite interval capital T, and you can bring you can thought of x tilde t to be equal to xt in one period. So you see, if you are going to evaluate the Fourier coefficient, you're going to consider one period, right? I mean, over here in this equation, if you consider the Fourier analysis equation, this is over one period, but over one period, in this range of time, x tilde t and xt are the same. There's no difference. Okay, because there's no repetition here. There's repetition here, but in this finite duration of period, which is capital T, there's no duration between xt and x tilde t. Therefore, you can easily replace this by by xt. So we are not putting x tilde t. This is xt. Okay, and since this is 0, xt is 0. Okay, now we are not putting tilde over here. Now we are just taking it from xt forward. Since xt is 0 beyond this limit minus t1 to plus t1, we can also without losing any generality, we can put the limits of integration from minus infinity to plus infinity. Okay, so outside this interval xt is 0, so we can write the integral limits as such, right? These are the Fourier coefficients for x tilde t, which is written in terms of xt. Therefore, defining the envelope, we define the envelope xj omega of tak as, now you bring t on the other side to the left hand side of the equation, this becomes tak, and this function is now being called as x of j omega, where x of j omega is your xt e to the minus j omega t dt. Okay, so tak is basically now the envelope of all the Fourier series coefficients, okay, which are now bunched together, close together, because we are considering x tilde t to be equal to xt with when xt is aperiodic, having infinite time period. Okay, so the coefficients of ak, they can be written as such: 1 over t xj omega, which is equal to 1 over t minus infinity plus infinity. Okay, these are the Fourier coefficients. Or you can write this as if you express this omega in terms of k omega naught, you expand that, k omega naught comes over here as well. So these are the Fourier coefficients. Now combining the following two equations, these two equations, these are the Fourier synthesis and these are the Fourier analysis equations, we can express x tilde t in terms of xj omega as so x tilde t is again your Fourier series. You recall that this is your Fourier series expansion. Okay, x tilde t was the Fourier series expansion, which is written over here as well. Then you just bring this ak over here, just substitute this over here, and this is what you get. So this is 1 over t, and then you have the envelope xj k omega naught into ej k omega naught t. This is the Fourier Fourier series synthesis equation for x tilde t in terms of the envelope of the signal. Now, equivalently, omega naught is also 2 pi by t. So, well, you can multiply and divide this by 2 pi by t. So, if you multiply this by 2 pi and divide this by 2 pi, you do little mathematical artifice over here. So, this thing becomes equals to omega naught. Okay, and you can take omega naught over here as well. So, this is written over. This is this expression. We'll have omega naught here, and you have 1 over 2 pi outside of the summation. Okay. Now, as t goes to infinity, x tilde t approaches xt, right? I mean, as t is going to infinity, there is no difference between x tilde t and xt, right? So, as t goes to infinity, then x tilde t approaches xt, and consequently, the limit, the above equation becomes a representation of xt. So, if I put the limit over here in the expression that t is going to infinity, then this representation is not of x tilde t, this becomes equal to xt, right? The expression becomes equal to xt, where omega naught becomes infinitesimally small quantity, so this becomes equals to d omega, right? This becomes a differential operator, and a natural call it a natural extension of summation operation becomes an integration. This has to be replaced by an integration, right? So this will be, again, in general from minus infinity to plus infinity. So the expression you are going to get is this one. So xt is 1 over 2 pi. 1 over 2 pi was here. Then xj omega, ej omega t, where k omega naught is omega, into d omega. So you see, from the envelope, you are recovering your original signal back. Or in other ways, you are expressing xt again in terms of complex exponentials having the weightage of xj omega by 2 pi. Isn't that right? So you see, for aperiodic signals, these are the Fourier coefficients now. These are the weights of your complex exponentials. So furthermore, as omega naught approaches 0, t approaches infinity, the right hand side of the above equation passes to an integral. This is what we have seen over here as well. So this can be seen by considering the graphical interpretation of the equation now, and illustrated in the figure shown in the next slide. So okay, let's go to the next slide. You see, over here we have x j k omega naught, e j omega naught. This is k omega naught, k plus 1 omega naught. So the area of the rectangle, I mean, is becoming very small. So this omega naught becomes differential and becomes the area under this rectangle. So this is the integrand, and this becomes the variable of the integration. This is basically the area underneath this xj omega and ej omega t at omega equal to omega naught. Okay, so each term on in the summation on the right hand side is the area of the rectangle. That's the height of the rectangle is xj omega naught, ej omega naught with width omega naught, and t is regarded as fixed. Okay, t is regarded as fixed. So as omega naught tends to 0, as omega naught becomes very small, the summation converges to an integral ej omega t. Therefore, using the fact that x tilde t is xt, as t goes to infinity, we see the above equation becoming taken in integration form, where xj omega was defined earlier as the envelope of the Fourier coefficients given as xt e to the minus j omega t dt. Okay, so these two equations are now referred to as Fourier transform pairs. Okay, in general, for an aperiodic signal, there's no reason that they are not representing a periodic signal. Well, they are representing periodic signals as well, but this represents a broader class of signals which are not periodic, but they can be aperiodic as well. Okay, so the above equation are referred to as Fourier transform pairs, and the function xj omega is referred to as the Fourier transform or the Fourier integral of xt. Second equation is the inverse Fourier transform. So second equation is giving you back xt. There has to be one-to-one correspondence between the xj omega and xt. So for example, if the Fourier transform exists for signal xt, okay, that's denoted by xj omega, then if that is the case, then uniquely its inverse has to give you the original signal xt. So it doesn't matter which way you go, there has to be a one-to-one mapping between these two quantities. Okay, xj omega now is the envelope of the Fourier series coefficients, which represents the strength of the Fourier coefficients at the given harmonics. So it's in itself it is representing the strength of the harmonics contained in the signal, the frequency components. So there is no reason. I mean, either you can go a forward direction. So if you have x of omega, taking the inverse Fourier transform should give you uniquely back xt, not any other signal. Okay, there has to be a one-to-one mapping. If the Fourier transform are also known as, I mean, they occur in Fourier transform pairs, right? So it's an equivalent specification. Either you specify xj omega or xt. The forward and the reverse is should be well known. Okay, the first instance equation plays a role for aperiodic signals, similar to that of Fourier series for periodic signals. Okay, so since both represent signals, the linear combination of complex exponentials. For periodic signals, these complex exponentials, they have the amplitude Fourier coefficients. They occur a discrete set of harmonically related frequencies k omega naught, where k is varying from 0 to plus minus 1, plus minus 2, 0 being the DC quantity. For aperiodic signals, the complex exponentials, they occur at a continuum of frequencies. Okay, and according to the second synthesis equation, they have the amplitude xj omega. You can see xj omega divided by 2 pi. This into d omega is your amplitude of the complex exponentials over here, right? So in analogy with the terminology used in Fourier series coefficients for periodic signals, the xj omega of an aperiodic signal xt is commonly referred to as the spectrum of xt, as it does provide us with the information needed for describing xt, the linear combination, specifically integral of a sinusoidal signals at different frequencies. Okay, so but again, I mean, even if you have a periodic signal, so if xt is periodic and you are representing this by Fourier series expansion, there is no harm in taking the forward Fourier transform. Let's say, I mean, you have to evaluate the Fourier transform in the forward direction, provided you accept that exponentials signals which are the Fourier transform in terms of impulse functions, because these are complex functions. Okay, and they have one. You see that for real signals, you have symmetric Fourier transform, but this is for one-sided. Okay, I mean, this does not have e minus j unless k is varying from minus infinity to plus infinity. So if it is one-sided signal, then your x of omega will be of the form, basically there will be a summation, so let's say 2 pi will be of the form summation ak, then there will be delta functions. Okay, so we will have delta functions. So this will be omega, and this delta function is in frequency domain, minus omega k omega naught. So this is the form of the Fourier transform. So don't believe that the Fourier transforms is a representation of aperiodic signal in terms of complex exponentials. Fourier transform, they also apply equally well to the periodic signals. But for periodic signals, you know that the difference is that how we use Fourier series is just it's a representation in the same time domain in terms of the Fourier coefficients, right, which are the strengths of the harmonics. You can also take the Fourier transform of such a periodic signal. You see the Fourier transform exists of periodic signals as well. So Fourier transform does represent both periodic and aperiodic signal. It does represent a broader class of signals as compared to Fourier series, but the representation is in the same Fourier framework. The representation is again in terms of the complex exponentials as Fourier has done in his work. So basically this framework is quite connected, but Fourier transforms, they are the representation of a broader class of signals in terms of complex exponentials. So based on the above development, now or equivalently on the comparison of Fourier transform with Fourier series, we also note that the Fourier coefficients AK of periodic signals can be expressed in terms of equally spaced samples of Fourier transforms of one period of x tilde t. So specifically suppose that x tilde t is periodic signal with period t and Fourier coefficients AK, then let xt be a finite duration signal that is equal to x tilde t exactly over one period, say. So for, let's say this period is from, you take the finite time period s to s plus t for some value of s, and it is 0 otherwise. So if you compute the Fourier coefficients of x tilde t by integrating over one period, so this is your integration limits, then x tilde t corresponds to xt in one period, right? So xt is 0 outside the range, so we can, by the same reason, we can express the integration minus infinity plus infinity. So we can write this as such. We can write in terms of the Fourier series coefficients, integration limit from minus infinity to plus infinity, because xt is only existing over the same time period, which is there in just one period of x tilde t. So comparing this with the Fourier synthesis equation, it yields that AK, which is the Fourier coefficient of x tilde t, is 1 over t x j omega, with omega being equal to k omega naught t, right? So you can see this development is very similar to what we have discussed previously, right? So well, if you that basically that's how we initially started out our discussion when t was infinitely large, and in that case xj omega becomes the envelope of the Fourier coefficients. Okay, so basically this thing is your xj omega over here as well. So AKs are a1 over t xj omega. So where xj omega is the Fourier transform of xt, and it states that the Fourier coefficients of x tilde t are proportional to the samples of the Fourier transform of one period of x tilde t, right? So for one period of x tilde t, we have the Fourier coefficients AKs, and these are the samples. So AKs are the samples of x omega, which is the Fourier transform of xt. Okay, so AKs are the Fourier series coefficients, which are representing the strengths of the harmonics, and xj omega is the envelope function of the such Fourier series coefficients, AK being the sample of xj omega. So this spec is often used in practice, and that's the matter of fact. That's what we have seen over here as well. I mean, the envelope shape remains the same, but in all these three figures, you see these Fourier coefficients are the samples of your envelopes, xj omega. Okay, that's the development, how the Fourier transform is developed in Fourier series connection. Okay, that's all.